Okay. Right. So this is the last theorem. I haven't given any proof yet. So I will start with today's lecture by giving a proof of this proposition. Okay. All right. So for convenience, we let random vector capital X as the vector with x1, x2 up to xn as component. Okay. And capital Y, the same, is the vector formed by y sub i's. And vector x, okay, represent a point in the n-dimensional Euclidean space. Okay. Okay. All right. So we know the joint PDF of x of i's is 0. Okay. Almost everywhere outside the open set D. So we have, of course, okay. The random vector is in D. So this event occurs with probability 1. And then the probability that Y is in GD. All right. So we now look at this event that the new random vector capital Y is in the image of the open set D under the coordinate transformation capital G, but both G, sorry. Okay. And so, but Y by definition is G of X, okay, it's in G of D. Okay. And so this is saying that, right, so the reason is that G is 1-to-1, okay? From D to, from 1-to-1 from D on to GD, okay? By the definition of coordinate transformation. So this 1-to-1. So G of X is in G of D, if only if random vector X is in the open set D. And this is 1, of course. So we know that the probability, so the distribution of this random vector Y will concentrate on the image of G under the coordinate transformation, both G. Okay. Right. So this is first observation we have. Any questions? All right. So our purpose is to show that the random vector Y has a joint PDF. Okay, right? So we have to. So now we let QY. Okay, defined to be the region. Okay. So this is the Cartesian product of semi-infinite rays in each coordinate. Okay. In two dimension, this is just so this is just equal to this part. So if here we have y1, here is y2. Okay. So this part and this point is y1, y2 in R2. Okay. So if n equal to 2, then Q sub y represent this region. Yeah. All right. So now the CDF, the joint CDF of y sub i's, okay, the joint CDF, this is equal to the probability that the random vector y is in the QY. Okay? Any questions? If you think this is too quick, then by definition, all right, so this is the legitimate definition of the joint CDF of y sub i's, right? And so this is P. So we collect them together. All right, so y1 would be in this infinite interval, and the y2 is in this infinite interval, etc., up to yn. Okay, so you can represent this joint event by using such a notation, using the vector notation. Okay, and so this is y is in Q y. Okay, by our definition. Okay. Any questions? Okay. All right, so probability of y in Qy, this event intersect the total event, not equal to the event with probability 1, so this is equal to GD. Right? Because this event has probability 1. And this is actually can be written as, okay, this is the same. Any questions? You may argue with me that this should be equal to intersect by decomposition. Right? This event intersect the complement of this event. The complement of this event would be G is not in GD. Okay? Right? Okay? Because the total event X, the sum space is a union of this event and this event. Okay? So by decomposition formula, the probability of this event becomes to the sum of the probability of these two joint events. But as we know, this intersections, though, so this is less than probability of not in GD. Okay? But what is this? This is 1 minus the probability y in GD. Okay? And this is 1 minus 1. It's 0. Okay? So this probability is 0. It's upper bound by 0, and probability always non-negative. So this term is 0. So you got the lesson. And if you intersect with an event, which event has probability 1, all right, then this joint probability will be the same as the original probability of this event. Okay. All right, so now we have such things. Okay. Okay, so now we can so that when we apply H of intersect GD, okay. H is also 1-to-1 from GD onto D. Okay? So before we apply the coordinate transformation H, because the coordinate transformation H only defined in G of D, right? The domain of H is G of D. All right, so without restrict, go to here, because this one, this subset, this set is a subset of G of D, right? But the QY may not be a subset of G of D. May not be. So that's the reason why we have to restrict, right, by using this argument here, so that before we can apply the inverse coordinate transformation H, we have to see, okay, to make sure that this is a subset of the domain G of D. Is that okay? All right, and then this is X, right? This is X. All right, and the H, Q, Y intersect GD. Okay, so we do the argument. We haven't applied any joint probability density function yet, right? We just do some argument on the high level. And now the last steps. Because X, right, this is about an event about the random vector X. So we can do the integration. All right, and the f of x, theta x, and the d of theta x. Okay? Now here. And then we call our change of variable theorem, the proposition 6.7.8. Now we can apply that, okay? So this is becomes true. Okay, so now we will let x to be h of y. Okay, this is so-called change of variable. And so the differential, okay, becomes to the Jacobian of h y here. And you have to take the absolute value of the Jacobian determinant. Remember, okay, in our change of variable theorem. Okay, I believe you take your notes last week. So, all right, and so now because of that, so x is h of y, right? And we integrate x in this range, right? H of something. So that the integration, so you can remove for h. So now this is q, y, intersect GD. Right? So it's so convenient because if we're already here. Okay. So y will be in this region already. Okay. And we have h of y. Okay. So this is change of variable. And we have a Jacobian hy and the dy. Wow, so nice, right? So what is that? By proposition 6.7.8, right? Change of variable formula. Okay, and then we can have qy and f of x h of y Oh, I think I make. I think I better to use not y because y has been fixed already, right? So I'm sorry, I have to use z. Okay. Z. Okay. Sorry. So Z. So the dummy variable should use Z here. Okay. And so this is Z. And dz. Okay. Okay, since f of x h z is 0 for all z not in GD. Okay? Oh, no. I think I can't do so. Sorry. Erase that. Okay, I stop. I should remain here. Okay. So okay, so which shows that y1, y2, up to yn. Are jointly, absolutely. Continuous random variables with a joint PDF fy little y. Maybe I will say I use z. Okay, I use z to be f of x and h of z. Okay, and the Jacobian h of z. Okay, for all z in GD, and 0 for all z not in GD. Okay, so and so that intersect GD complement f G and so I will say 0. Okay, is that okay? Okay, sorry. right? So this part, because that the h function, all right, only defined on G of D. Outside G of D, h has no definition. Okay. So this part, so that Q the QY intersect with GD, so this is fine. But for Z outside of GD, all right, then so this part should be 0, right? Because the formula is here, and so this becomes to QY and f of y z and dz. Okay. Okay. So the missing part. So this is. So we find that we start. So the joint CDF. Okay. Because our purpose is to find, so if it has a joint, if the y vectors, the random vector y has a joint CDF, that means that if it's absolutely continuous, then we should find something. Okay. So the question is, can we find such okay? So our question is that, can we find this one, right? A joint PDF, such maybe I would say joint PDF for all z in Rn, right? So the question is that, and here up to here. So maybe I will. So this one is makeup, right? Because what we have up to this one. And so we have to resolve the problem that the joint probability function of capital Y, what is the value of joint probability function outside the G of D? Okay. And from our previous lesson, we know that when Y outside of G of D, the probability is 0. Okay, so we have the confidence that, right? So this is, so we just add this 0 integral. Okay, the value is 0, right? Right, and so this will become to be consistent. Okay, all right. So the sum of this integral becomes to a single integral, and the integration region will be Q of Y. Okay. So this is Q of Y. This is what we want here, Q of Y. And the f of yz should be defined in this way. When z is in G of D, then of course this should be this integral. But when z is outside of G of D, okay, so it's outside of G of D, so maybe I will say outside of G of D, complement. Then the value of this joint PDF should be 0. Okay, so altogether, so this, okay. Okay, so match. So everything has been done right now. Any questions? So even though we make up this part, but it's significant, has a significant meaning for this zero integral. Okay. Because from that, we know that a proper definition, okay, for the joint PDF of random vector y should be like this one. Okay, and this definition, the finding, is coincident with our finding there. Okay. Any questions? The proof is neat. You can see not many formula you need, right? But the argument here is very important. Okay, the argument here. The central things you have to keep in mind is that the inverse coordinate transformation H defined only on G of D. Okay, it is not defined on the whole n-dimensional Euclidean space. No. No, in practice, no. Okay, only defined on this subset G of D. This is the reason why we have to do several steps before we can apply this integral. Okay, and then we can do that because we want to apply change of variable. Okay, so we want to apply change of variable, and so we have to make sure that this inverse coordinate transformation only apply to G of D. Okay. Personally, I think this is the shortest proof. Okay. Okay. Yeah. You can compare other proof in other textbook. Our textbook doesn't provide any proof. I think so. Am I right? Anyway, but okay, so there is one extension. Okay, just like we have done for functions of single random variables. Okay, so so again, x1, x2. All right, x1, n jointly, absolutely continuous random variables with a joint PDF such that equal to 0 almost everywhere outside an open subset D of Rn, i.e. the probability that random vector x in D is with probability 1. Okay, so I will use the notation freely here, right? The vector notation freely. Okay. Okay, so this is about random vectors. How about the transformation? Okay. So a vector function from D into Rn, or it's already Rn, so just a vector function on D is enough already. Okay, so G is not required to be a coordinate transformation. Okay, when just a vector function on D. Now we assume that D is a union, all right, of countably many disjoint open subset. We call DI such that for each I, the restriction G on DI of G of the vector function on DI, okay, it's a coordinate transformation. All right, so we assume this open set D can be decomposed into countably many disjoint open subsets. Open subsets. Right. And in each piece, in each open subset D sub I, the restriction of G on DI, so this function, this restricted function, is a coordinate transformation. Okay, so in each piece, D sub I, the G function becomes to a coordinate transformation. Okay? Now we let H sub I be the inverse transformation of G restricted to D sub I. Okay? On G of DI. Then y1 equal to G1 x, y2 equal to G2x, yn equal to Gn x, right? So these n new random variables are jointly, absolutely continuous random variables with a joint PDF. Okay, so this joint PDF becomes to f of y, little y, is equal to summation of j, f of x, h I sub j, y, absolute value of the Jacobian determinant of h sub I sub j, y, okay, and this is f of x, h I sub j, y, and Jacobian of the g at h I j, y here. Okay, for all y in G of D, all right, where I sub j are all indices such that y is in G of D sub ij. Because that maybe there are a few p's D sub ij, right, were mapped to, right, and this range will contain the same y. Okay. Okay. And for all little y, not in G of D, then the joint PDF would be 0. Okay. So the expression is quite similar to we have obtained in chapter 5 for functions of a single random variable. Okay. And you will see that the theorem provided in chapter 5 is a special case of this general theorem. Yeah. Okay. So proof is as an exercise. Okay. So you can apply the similar method, the similar proof we have given for proposition 6.7.b. Okay. Any questions? Okay. Okay. All right, so we finish chapter 6. Now we come to the longest chapter in this semester. All right, I will talk about a lot on the properties of expectation. Okay, including conditional expectation. Okay. Right, so in this introduction section, we will review some of the concepts we obtained before. Okay. So recall, for a discrete random variable x with probability mass function p, little p of x, the expectation, all right, E of x, the expectation of x is defined as here provided the sum exists including, for example, if the discrete random variable is non-negative, then such a sum will always exist, but maybe infinite. Okay, diverge to infinity. Okay. So if x is a discrete non-negative random variable, then expectation always exists, but maybe infinite. Okay, so you have to distinguish whether the expectation is finite or infinite. But if x is a general discrete random variable, positive, negative, or zero value, maybe, then the expectation may not exist. Okay, may not exist. So so you have to justify that. But as before, you can decompose the x into the positive part and the negative part, right? And then to find the expectation of the positive part and the expectation of the negative part, and to see if both of them are infinite. If both of them are infinite, then the sum does not exist at all. But if at least one of them is finite, then the sum exists. Maybe positive infinite, maybe negative infinite. Okay. And the expectation exists and finite if and only if the positive part and the negative part both have finite expectation. Okay. All right. So as we done before. So when I say provide the sum, oh, I'm sorry. I'm sorry. Okay. The sum, not the sum. Okay. Exists. All right. So this is for discrete random variable. Okay. And it's understandable that the sum is countable because as we know, it's discrete, right? So only countable many values such that p of x is positive. Okay, all right. So the sum would be basically it's a countable sum. All right, and recall for an absolutely continuous random variable x with PDF f of x, the expectation of x okay, of x, the expectation of x okay exists and is finite provided that the integral converges absolutely, i.e. if this integral, okay, so if we take the absolute value of x is finite, okay. Because f of x is integrable and the absolute value of x function is also integrable, and they are non-negative, so this integral always exists. Always exists, but may be infinite. Okay. So if it is infinite, then we don't know whether this expectation exists or not. We don't know. Okay, we don't know that. But if this integral is finite, so we say this integral converges absolutely. Absolutely. In this case, then this integral exists and is finite. Okay. All right, and so recall from corollary 5.2.d for any random variable x, the expectation it's equal to the difference of two integral minus okay. Provided that at least one term on the right is finite. Okay, so either this is finite or this is finite. Then the expectation will be equal to this difference. So the value can be positive infinite or negative infinite. All right. Or maybe finite if both of them are finite, has finite value. Okay. Okay. So this is we obtained in chapter 5, right? To have. All right. So and another general result. So recall corollary 5.2.e for any random variable x with CDF. So if we know the CDF, the expectation of x, so the expectation of x is expressed, so can express by the Riemann-Stieltjes integral. This exists and is finite, provided that the Riemann Stieltjes integral converges absolutely. Which means that if the integrand becomes to the absolute value of x, okay, then this will be finite. So this is what we have from previous chapters. Okay. And we can obtain a simple property, right, which may be useful in some applications. So a simple property of expectation saying that if we know the random variable x has valued in the course interval from A to B with probability 1. Okay. So where A, B are real numbers, then the expectation of x also bounded up by B, down by A. Okay? This is a very simple factor. Okay. The random variable may have value outside of this closed interval, maybe, but the probability for that event occur is 0. Okay, so this is just show that the random variable will have value in the closed interval A to B with probability 1. Okay, if this is true, then the expectation of X, this is just some specific value, right? It's a real number, and should be a real number between A and B. Okay. All right, so let's give a proof for that. All right, so so things is 1. The CDF f of x over x is, so we can see that f of x equal to it's 0 when x is less than a. Okay. Maybe I would say would be less than equal to complement, right? When x is and this is so if x is less than a, okay, then so this infinite interval would be outside of the closed interval, a, b, okay, outside of them. It's here. So if x is here, okay, so this infinite, oh, sorry. X, and the x is less than a. All right, so if x is less than a, then this interval is outside of this closed interval. So that this is contained in here. All right, but this probability is 0. 1 minus 1 is 0. Okay, so that means that f of x is 0. Okay, because CDF always greater than or equal to 0 and upper bound of 0, so that f of x is 0 for all x less than a. And f of x is up bounded by 1, right? And which is okay when x is greater than b. So if x is greater than b, then this part will include AB, right? So this infinite interval will include this open interval, this closed interval, but this is equal to 1 already. Okay, or maybe so when x greater than b. Okay, so that f of x is also constant equal to 1 for all x greater than b. So it's very interesting that if you draw, if this is A and this is B, for example, then that this is 0, okay, up to here, and from B, 0. Okay, and we don't know here. So this is f of x. Okay, so in between A and B can be arbitrary. Okay, but we're sure that if x less than A, then it is 0. If x greater than B, then the value is 1, for sure. Okay. Okay, so now since we compute this Riemann-Stieltjes integral, okay, we'll compute this Riemann-Stieltjes integral, and this can be decomposed into from infinity A plus AB plus B to infinity okay. All right, so this integral decomposed into 3 integral. In this interval, the value of f of x is 0, constant. Okay, so the integrator, the differential of the integrator is 0. Okay, so this is 0. Similarly, this is also 0 because the CDF in this infinite interval is equal to 1, it's constant. So the differential becomes to 0. Okay, so the first and the third Riemann-Stieltjes integral is 0 because the integrator, these two integrators are constant. Okay? All right, so they are constant, right? And so only this part. Now, but because x is in this range, so the absolute value would be less than upper bounded by the maxima of A and B. Okay. And the df of x. Okay. So when x is in this range, the absolute value of x will be upper bounded by the maximum of the two endpoints. Okay. And why is that? This is the maxima of A, B. All right, and df of x. Okay. So, and this is equal to 1. So this is maxima. So this is equal to 1, as we know. So it's finite. Okay. So that the Riemann-Stieltjes integral converges absolutely. Okay. Okay. So this is finite. And so now, so E of x exists and is finite. Okay. And we can compute which is okay, it's equal to this Riemann studio integral. And again, you can decompose into okay. Right, and this is 0. This is 0. Okay, so here we have AB, x, and the df of x. Okay, so lastly, now since A so for all x in this cost interval, we have A to be the lower bound and B would be the upper bound. And so the integration okay. And this integral is equal to 1. This integral equal to 1. And as we know, this is equal to expectation of x. So finally, we have all right. So let's take a break of 5 minutes up to 2:40. Okay. Yeah, huh? Okay, so now we will talk about the subject of expectation of functions of several random variables. We talk about expectation of functions of single variables in chapter 4 for discrete random variable and chapter 5 for absolute continuous random variables before. Okay, so proposition 4.4.1 says that if x is a discrete random variable, taking on the values a sub I, okay, for I in the index say capital I, and the G is a real value function on R. So arbitrary real value function may not be piecewise continuous, just arbitrary, okay? For discrete random variable, this is very general. Right? And then the expectation of g of x, x defined here. Of course, that I think, well, okay. Because g of x, the new function is also discrete, and the expectation of g of x and x equal to I, little I in I, and the g of ai, and the little p of a sub I. Okay. Or sometimes we just write provided that the sum exists. All right. Of course, here P of x is the PMF of x. So if we define this to be y, it's a discrete random variable too. Okay. So it's simple, right? If x is a discrete random variable, then the data processing function G can be arbitrary function, any real value function, so that when you do the data processing under G, the process the result g of x defined to be y is also a discrete random variable. Okay, so we can have that, and we proved that in chapter 4. Okay. Okay, now the xy two discrete random variables taking on the values A sub I for I in index I, and B sub j, j in the index j. Respectively. Okay, so AI are possible values of discrete random variable capital X, and the B sub j are possible values of discrete random variable capital Y. Now we have a data processing function, which is an arbitrary real value function. Okay, on R2. Okay, so it's arbitrary real value function R2. Then Z defined to be G of XY. Okay, it's a discrete random variable. Okay, and the expectation of Z equal to GXY is, so expectation can be expressed by double sum G AI BJ P AI BJ, and also can be represented by this generic sum. Okay, provided that the sum exists, and where Pxy is the joint PMF of X and Y. Okay. So you can see this proposition is an extension of proposition 4.4.1 to two random variables jointly disputed and described by their joint PMF. Okay, so the proof. Now, maybe I'll start from here. Since I and J are countable set, the Cartesian product of I and J is also countable. Okay. That's possible values of Z, which is G of XY, are the set G of AI Bj. Okay, so for every I and J, you have a value, right? And the pair I, J ij pairs is in this Cartesian product. Okay, it's in this Cartesian product. Remember, Cartesian product by definition is the ij pair such as. Okay, so Cartesian product is just the set of all pairs of ij. Okay, and so that maybe you have different ij pair, but with the same g values. So it's possible. So note that it is possible that ij not equal to I prime, j prime, but GAI bj is equal to GAI prime and bj prime. Okay, so it's possible, right? It's possible. So in this set, you may have multiple count, but as I say, the same element will be regarded as only one element. Okay. All right. So possible values of these new random variables are in. Oh, I'm sorry. In this set. And since the size of this set is less than or equal to the size of this set, this Cartesian product, AI, Bj, I in I, J in J is a countable set. Okay. So it's a countable set. Okay. So this set is countable, and this set has a size less than or equal to this countable set. So that is countable. Right. So this shows that Z is a discrete random variable. Okay? So it's a discrete random variable. Oh, not yet. I'm sorry. So for each, no, I'm sorry. And we let CK equal to with K countables index set. Okay. Now we have that ready. Any questions? Now for each k in the index say capital K, we let I would think a good notation. So I would say maybe I use QK. Okay, is equal to IJ such that G of AI Bj is equal to CK. Okay. As I mentioned, different pair may corresponding to the same function value here. Okay, so that I will, for each little k, I will collect all the ij pair such that G of AI Bj is equal to C sub k. Okay? Which is a countable set. Okay? All right, and so now Z equal to CK. This equal to CK. Is the disjoint union of I, J in QK such that X is equal to AI and Y equal to Bj. Okay. I'm not so sure. Do you have any question about this identity? If no, then I will go over that. If yes, then I will explain that. Yeah. Well, if you are not comfortable. Okay, so I will show here. Omega in Z equal to CK. All right. So an outcome is in this set because I want to prove this is an event of interest. An outcome is in this set if and only if the Z of omega is equal to CK, right? So that is definition. And so this is that. This is saying that the G of X and the Y, okay, of omega is equal to CK because Z is G of X, and this is saying G of X omega, Y omega is in CK. Okay? Now, and that means that, remember that this two, if we have an outcome, then this is a real value, okay? Because it's a real value, random variable, a real value. And they are possible values. So x of omega are some AI, right? Y of omega are some BJs. And when this is the case, so this is saying that S omega and Y omega, the pair must be equal to AI BJ with IJ pair where? In the QK. Right? Because from our definition, you see that you have the G function equal to CK. Whenever you have AI, BJ, and IJ is in the QK, right? You collect them together. So the possible way for X and Y together to give you the process, the result is CK, is whenever the AI pair, this is AI and the BJ pair, such as IJ is in QK, from definition. Okay, and so once again, so this means that X omega is in AI and Y omega is in BJ with IJ is in QK. So that means that omega is in X equal to AI, and omega is in Y equal to BJ with IJ in QK. Okay? Is that okay? So X has this value and Y has BJ value. So omega is in the joint event. Okay? Because end. So X must be in the intersection of these two. So intersection can be described in this way, right? This is the same as saying that intersect. Okay? With IJ in QK. So this is saying that omega is in the disjoint union of IJ in QK of X equal to AI, Y equal to BJ. Right? So we prove that when outcome is in this event, in this subset, then outcome will be in the disjoint union of this subset. So we prove that Z equal to CK is equal to the disjoint union of X equal to AI, Y equal to BJ. And this must be in the sigma algebra. Why? Because X and Y are random variables. So So this is an event of interest. This is an event of interest. So their intersection is also an event of interest. And now you take a countable union, because Q sub k is a countable set, right? Already, we just shown. So this is a countable union of event of interest. Okay, so this is in F, right? In the sigma algebra. And the countable union is also in sigma algebra, because sigma algebra is closed under countable intersection, countable union, right? And it's closed under the complement. This is set operations. So this is in the sigma algebra. Okay, so in here, up to now we can say Z is a discrete random variable. Up to now we can say that. After we prove that this is actually an event of interest. So to show that it's an event of interest, you have to go through this argument. It's not so trivial, okay? Even though we are dealing with discrete case. Discrete case is relatively simple, right, up to now. At this point of the semester, we are now in 2/3 of the semester already, right? Okay, so now we prove these are discrete random variables. So the strategy is here. First of all, we show that possible value of Z, right? The set of all possible value of Z is countable, okay, by using this argument. And then the second thing to show, for each possible values, this subset is an event of interest. Okay, by showing that it's a union of event of interest already. Okay, so this is the discrete random variable. Okay, and so, and from that, and this is very important, because that we have a disjoint union. So the probability, so now we are using the countable additivity of probability function, right? And so we have the probability of Z equal to CK becomes to the sum, okay, for all ij pair in QK, all right, of the joint probability. Okay. That means that the PMF, all right, the PMF, the probability mass function of Z is the sum can be expressed at the CK, at the possible value CK, is the countable sum of the joint PMF of AI, Bj. Okay? Now, we have this sum. This is very important. It's very important. Now, so thus, we have, so the expectation of Z, by definition would be K in capital K, right? Of the CK and PMFZ of CK. That's our definition, right? Because Z, we have proof that Z is a discrete random variable already. And the possible values are CKs. Okay, so that by definition, the expectation of z is equal to this one. Is that okay? And so, CK. Now we apply this formula. This is the summation of Ij in Qk. And the P of xy, Ai, Bj. Now you move Ck into the inner sum. You move Ck into the inner sum. Okay? When you move into the inner sum, you can replace Ck by what? Because Ij is in Qk, by definition of Qk. By definition of Qk. Qk consists of all pair of index such that Gi, Bj up to the data processing function G equal to Ck. Okay, so in here, Ck can be replaced by Ai, Bj, or Ij here, right? Only in here, not here. When we move the Ck inside the inner sum, we can replace it this way. Okay, so now we have K equal to the bigger K and the Ij, and we have G, Ai, Bj, and the P, xy, Ai, Bj. Yeah. Now the sum, the double sum exhausts all possible Ij pairs, right? And so this becomes to I in I, J in J of G, Ai, Bj, and little p, Ai, Bj. And this is expectation of. So this is what we want. What's the formula here? Okay. And finally, we can use the generic okay, so provided the sum exists and is finite. Okay. Okay, I think exists is okay. Okay, so we have done here. All right. So this is a proper way to show the result. Even this is a very simple result. Look like very simple, right? Because the random variables are so simple type of random variables. But if you want to do the proof right, you have to go through this procedure. Okay? So it's a review of all the concepts starting from chapter 2. Right? We go back to chapter 2 already. Remember, our final examination will cover the whole book, right? Whole range. So you have to have everything in your mind and ready for the final examination at that day. Okay. Right. So you can think about this chapter is a review of the stuff, and then we will go deep to some important result. Okay. And I try the stop not so deep. Okay, slowly, but at some point it will dip. Okay, I'm not so, I cannot guarantee, but I will provide useful results. Okay. Today the slope is very slow. Okay. So it's an opportunity for you to review some of the basic concepts. Okay, from the beginning of this semester. Any questions? Okay, so if no question, and then I'll stop here and see you on Thursday. Yes. 好，请说。